Welcome and hello. This is a video exercise in WRIMS, and in this exercise, we're going to be dealing with water supply reliability. That refers to the percentage of times someone who has a water demand or allocation actually receives that water. So this is a very simplified example we're going to see with a few if-then statements and scenarios we're going to look at towards the end. All right, what I have on the screen now is a very simplified schematic of our water system. At the top, we have a reservoir, which has an inflow, a storage, and then nodes 1 through 4, or no, 1 through 5, representing the main channel flow. This is the main river. And then we have diversions to farm 2, 3, and 4, which come off of nodes 2, 3, and 4. And those farms each have a demand, which is denoted by these variables dF2, dF3, and dF4. There's also an in-stream flow demand, D5 down here. All right, in this slide, I've grayed out some of the previous variables, and now I'm showing some of the decision variables referring to the channel flow. So C12 refers to the flow rate in channel 1-2 in the main river between from node 1 to node 2. Same thing with C23, 3-4, and 4-5. Now, this diversion flow, C2F2, that refers to the flow rate in CFS from node 2 to farm 2. And then the same thing is true for farms 3 and 4. All right, what I'm doing down here for C45, I'm actually going to divide this up into two different parts, and you'll see this when we actually get to the constraints and start writing in the Russell code. But this C45 right here, the flow downstream of node 4 to a hypothetical node 5, is going to be comprised of the sum of C45 min and C45 extra. That will allow us to add C45 min to the objective function, as well as set it to a maximum of that downstream demand. All right, what I have on this slide over here to the left is a table, and it shows the demand in the left column, and then the priority and the allocation, or the total amount of water. I've ordered this table in order of increasing priority. So top priority is at the top, which is D5, our in-stream flow. And then priorities 2, 3, 4, 5, 6, and 7 refer to the different farms. So farm 2, for instance, has priority 2, and they have priority 5. Now with priority 2, they have an allocation or a demand of 2 CFS. And then later down in priority 5, they have an allocation of 7 CFS. So each farm has two different priorities, and they're sort of scattered within this table. Farm 3, for instance, this is the one we're going to be looking at. So here I'm highlighting Farm 3. This has a priority 3 for 3 CFS and a priority of 6 for 8 CFS. We're going to be looking at Farm 3 in particular for this example. That's why I've got the Farm 3 highlighted. And I also wanted to point out that C3F3 is the flow rate through this diversion to Farm 3 to satisfy the total demand DF3. All right, in the next slide here, I'm looking at C3F3, and I'm dividing it into two separate parts, the same way we did that with the downstream demand D5. There's going to be C3F3P3, which refers to the amount of flow through C3F3 satisfying priority 3. That will have a max of 3 CFS, and then C3F3P6, which will satisfy the 8 CFS demand. That will have a maximum of 8, but that's down here at priority 6. All right, and then last slide for now here, we're dividing the demand DF3, the total 11 CFS demand, into two separate parts. It's going to be composed of the demand DF3P3, that'll be equal to the 3 CFS, and then DF3P6, that'll be equal to 8 CFS. And then down here, I have a constraint that basically says that the flow satisfying the P3 demand and the P6 demand cannot exceed the total demand. All right. So some of the decision variables that you're seeing in this slide here only refer to farm 3, but just keep in mind that all the decision variables and constraints will also have their own separate equations for farm 2 and farm 4 as well. So what we want to do in this exercise is determine what is the water reliability to farm 3. And there's also a number of different variables that haven't yet been defined. We'll look at that as we build our model, and that will begin now. Okay, so I've got Eclipse up and WRIMS. Let's go ahead and right-click, New, and start by creating a project. With General Project selected, I'm going to click Next, and then give it a project name, E8, Water Supply Reliability. I'm going to number this one 2 because I already have one up here. and then uncheck this checkbox and paste in the path to the project directory in this text box. Here is my project directory. There's nothing in here now, so I'm just going to copy the path and then paste it right in here and click Finish. All right, so here is our project directory. And the first thing I want to do is right click and create a launch file. So I'll come down here to Run As and then Run Configuration. All right, I'm going to select Russell/WRIMS2 application and then click on the New button. All right, so we have a new configuration we're defining. I'm going to give it the name E8 Water Supply Reliability up here. And then some of these fields I don't have to put in, like the description, author date. But what I do want to put in is the main Russell file. I'm going to create and save that file in a run directory and just call it main.wresl. All right, the three DSS files, I'm going to save those in a DSS directory, so dv.dss, and then sv.dss and init.dss. Further down here for part A, I'll just be generic and call it project. Part F for the state variable, I'll just call that state and init. All right, down here for the time step, we'll use 1 month. We'll use the start date that it's giving us here, and this is going to be a 100-year simulation. Now, we could make it longer. We could run multiple simulations. Let's just go with 100 year. So I'm going to select 2021, which is right here, and then leave everything else the same. So this is 100 years, 100 water years, and we're good there. Let's go up to the configuration tab and then make sure to check on this Russell Plus checkbox, the first one. And then the last tab we want to make edits to is the far right tab. So if you don't see the common tab, you have to click on this chevron and then click common and then click on the shared file and then the browse button and then browse and click on the project we just created, which is right here. Okay, so click apply and then we can click on close. And then what we should see over here in our directory, here it is. This is our launch file right here. So you can see it says .launch. Now I'm going to go ahead and just delete this extra project. I'm going to get confused if I don't. Okay, there we go. All right, let's go ahead and get started building our project in files. Right here is the project directory. This is what I want to create. So we have our project directory, and then I have created these two files already just by virtue of creating the project in WRIMS and creating a launch file. Now I need to create some directories like run, DSS, and system, and then add the files here and populate it, and then we'll actually run the model. All right, so here is the project directory. These are the two files that we have already. I'm going to create a DSS directory. So DSS, there we go. And then inside the DSS directory, I want 3 files. Those will be the 3 DSS files. So new, and then text document is what I'll type, dv.dss, and then delete the file extension, and then say yes, agree to the new file extension. Boom, that's ready to go. I'm going to hold down Control and just drag out a new file. It's basically a copy of this blank file. SV will be for the state variables. That's where we'll have the inflow. And then init is the last DSS file. That's where we're going to provide a model, the initial reservoir storage data. Okay, back up to the main project directory. Now I need to create a directory for run. Okay, boom. Inside the run directory, I need my main Russell file. So new and text document main.wresl. Okay. And then I also need a directory called system. So right click, new system. And then inside that system directory, I need to create 6 separate blank Russell files. And just as before, I created those blank files. So we have inflows, demands, channels, reservoirs, constraints, and objectives. We're going to go ahead and populate all of these files in just a moment. But what I want to first populate is if I go to my project directory, populate the data for the init and the state variables. So to do that, I'm going to open up DSS view and then open to navigate to those files. All right, here is my project directory. Here's DSS, and then here is init.dss. Okay, there's currently no paths, no surprise there. And then I'll open up my state variable file. And just for good measure, because I'm going to need to see it a little bit later in the video, let's open up the decision variable file. Okay, so the 3 files I opened up are right here across the top in these tabs. Let's start with the init data. To do so, I'm going to go up to the data menu and click on manual time series. And then for the path name parts, I'm going to paste in what I have prepared here. Project, storage in reservoir 1. Part C is going to be storage. It'll be a 1-month time step. And then init is the keyword that I specified in my configuration for init part F. So make sure you get that matched up right. All right, for the start date, I'm going to say 31 July of 1921, 2,400 hours. The is going to be in total acre feet, and then the type, I'm going to select period average. Now the storage in this reservoir is going to be 20,000 acre feet, so I'm going to type in 20 a few times here. Now the simulation is going to start right here on October 1921. So I really only need 1 month back because my code is going to reference only 1 month back. You can reference up to 12 months back, or 12 time periods, I should say, but it's typically months. That's what I've always done. I'm doing 3 months just to be safe and because I like the look of it. So as long as you have one here, that's good. I'm going to click save and we are good to go. So boom, here is our starting storage of 20,000 acre feet in our reservoir. All right, next what we need to do is specify the inflow data. So I'm going to head over to the sv.dss file right here. And just as before, I'm going to go up to the data menu, manual time series. In this dialog box, I'm going to paste in the path name parts I have prepared, similar to before, but not exactly. It's still project and it's still 1 month time step. This time part B is I_res1. That's just the name of the state variable for the inflow to reservoir 1. And then we have flow is the parameter. This time it's going to start at the same date as the simulation start, which is October 1921, 2,400 hours. The units is going to be in CFS because we're dealing with inflow. And then the type, again, is going to be period average. All right, now down below here, this is where I paste in my actual values referring to the flow in units of CFS every month. To do that, I've actually prepared a Excel to synthesize data for me. So what I have here is the year, the month, this goes down 100 years, and then the actual data I'm going to paste in. Over here, I've created a generator. So what happened is, here, let me zoom in a little bit. The first couple months are fixed at 110 and 115. And then I have an average flow for each month that repeats year after year. That's inflow. And then a standard deviation, which I just arbitrarily set to 10% of the flow. And then I have this noise right here. So the value that's calculated, not the first or the second flow, but flows 3 through 1200, follow this equation right here, which is loosely based on the previous 2 months, the average, the standard deviation, a random variable, as well as a noise amplifier. So anyway, that is the equation and it's copied down for all of these cells. So all I need to do is just recalculate and then boom, I have new values right here. So I'm going to just copy and then come over here and paste the values, boom. And then I'm going to copy these values right here in case I wanted to have these and these keep recalculating. I had them for myself. And then I will paste, boom, right there. Okay, so those values are pasted in. I'm going to click save and then take a look at this data. Here is a plot of the inflows over 100 years. So if I zoom in, we can kind of see the annual fluctuation of wet time of the year, dry, wet, dry. This is 1930. This is 1967. This is 1991. So that's the data. We can also get the tabulated version of those numbers right here. Okay, so let's go ahead and move on to defining the actual Russell files, which we need to define the actual system with our deep demands, our constraints, and our objectives. To do that, I'm going to navigate to my files. So we're going to run, and then here's the main Russell file. That is right here. I'm going to define the other files first. So let's just open them all up. In the system directory is where we have those other 6 files. So boom, we've got them ordered how I want. Okay, we're going to start with inflows. This is what I think makes the most sense to start with, inflows and demands. This is a state variable. It's I_res1. I've just pasted in here what it's going to be. The flow is part C of the path we created, and the units are in CFS. So this is all ready to go. That's all we need to do for the inflow because the configuration points to that sv.dss file. And then from there, it can read in part B and part C. All right, next is the demands. And here is the demands. This table right here reflects the different demands or allocations for the different priorities. So D5 refers to that in-stream flow. F2P2 refers to the demand to farm 2 with priority 2. And you can see that the actual value is 100 CFS, 2 CFS, 3 CFS. That should look familiar if we're looking at this table right here. So we have the name of the demand, and then we have that allocation right here. As far as the priority, we're going to see this come up when we define the objective function. So just hang on tight for that. But what we looked at was columns 1 and 3 in this table for defining these demands up here. Although not necessary, I also defined the total farm demand, which was farm 2, farm 3, and farm 4. Okay, that's just so it'll be calculated and show up in the db.dss file if I wanted to look at the total demand. All right, next up is channels.russell. And then here is the code for that. I'm just pasting in the code to save time. Otherwise, this video would be a lot longer. And I'm going to do my best to explain what each of these decision variables are. The top three here is the flow in the main river, just from the reservoir all the way down to node 5. The last channel in the main river is C45, which I've divided into a min and an extra. And we'll see in the constraints that minimum plus extra equals the total flow. Also, just like dividing up C45 into two separate parts, I've also divided up C2F2, the flow to farm 2, and then the flow to farm 3, and the flow to farm 4 as two separate parts, which means, say, we'll pick on farm 3, for instance, here. If I scroll, the total diversion to farm 3 is a combination of the flow related to priority 3 and the flow related to priority 6. And the reason I'm doing it this way is because I need to specify that the ceiling or the maximum flow C3, F3, P3 cannot exceed the demand for priority 3. And then same thing with priority 6. Okay, next file over is the reservoirs, and boom, here's the data. Our only decision variable is the storage. That's S underscore res1. So that's pretty straightforward. What's important about this is that sres1 and storage match up parts B and C when we were defining the initial storage, which is in this init.pss. See, we have part B, S underscore res1, part C, storage, and then also the part F, init, that needs to match with the init that I mentioned in the configuration. Okay, after that, the two state variables associated with the reservoir are right here. We have total volume of 25,000 acre feet, and then a target volume of 20,000 acre feet. All right, next up is the constraints. And you guys are going to hate me for this because there's a lot of constraints. So let's take them one at a time. This first group is labeled as continuity within the nodes for nodes 1, 2, 3, and 4. Node 1 is actually the reservoir. I just called it node 1 because it's at the reservoir and I wanted to keep the labeling similar. But what we have is the inflow to that node, inflow to the reservoir, the outflow, which is the flow through channel 1, 2, equals the change in storage, where we have our reservoir storage at the current time step minus the reservoir storage from the previous time step, hence the -1, and we also need that unit conversion. The other three node continuity constraints for node 2, 3, and 4 are pretty straightforward. It's the inflow minus the outflow. Okay, below that we have continuity for the channels. So as I mentioned, we have divided the flow through diversion to farm 2, 3, 4, and even the downstream in C45 into two separate parts. There's no storage. That's why the right-hand side equals 0, as is the case with a lot of these constraints. But basically, channel flow through channel C2F2 is divided into the sum of C2F2 priority 2 and C2F2 priority 5. Similar deal with farms 3 and 4. Okay, this last one is just to define the total demand, F2, F3, and F4, which equals the sum of the two separate demands that are allocations that each farm has. So with farm 3, for instance, we know this value is 11 because the priority 3 has an allocation of 3, and then the priority 6 has an allocation of 8. Okay, I realize that could have been hard-coded, but doing it this way allows us to make updates to specific demands and allocations in fewer number of locations, so it's a little bit more robust and user-friendly to set up the program like this. Okay, next is our max demands, which basically says like the flow through the channel C2F2 P2 cannot exceed the demand. And then same thing for all of the 6 priorities. That's all that's happening right here. And then further down, the downstream demand. Remember how C45 is divided into a C45 min and a C45 extra? Well, C45 min cannot exceed that downstream in-stream flow demand, which is 100 CFS. And then finally, we have a couple constraints related to the reservoir. Here is max capacity. So the current volume in the reservoir, S underscore res1, cannot exceed the maximum capacity of the reservoir, S1. That's what that means. And then we have our one and only soft constraint right here, which basically tries to keep the reservoir level at the target. And if there's any deviation from the reservoir's current level and its target, which we set to 20,000 acre feet, then there is a small penalty involved. All right, so that's the constraints. I'm going to click Save All, scroll up to the top. The next file over here is the objectives, and I'm pasting in what I have for the objectives. What we want to do is maximize all of these values here, which is the in-stream flow, as well as the delivery of flow to meet the demands to farms 2, 3, and 4, ranging from priorities 2 through 7. So if I bring up that schematic again, now we're dealing with the priority 1, 2, 3, 4, 5, 6, 7. Now the far left column is the demand, but the decision variable is the actual flow to satisfy that demand. So for D underscore 5, for instance, if I go back here, that is satisfied with C4 min. And then to satisfy demand C2 D2, that's satisfied with C2 F2 P2 and C2 F2 P5, the two different flows through channel C2 F2 to satisfy that C2 D2 demand. I think I said that right. Okay. So anyway, I'm just numbering the weights in descending order because the highest priority would have the largest weight or the largest multiplier coefficient in the objective function. All right, and the last file here is the main WRIMS file. This is called from the configuration to orchestrate the entire script. We're going to be running the inflows, demands, channels, reservoirs, constraints, and objectives by including those files in that specific order. And this was the exact same order that we talked about the files right here. Okay, so I'm going to go ahead and click Save. Let's go ahead and see if this runs and see what happens here. I'm going to refresh my project in WRIMS just to make sure I have my files. That looks good. And then right-click on the launch file, Run As, and we'll see what happens. Okay, it looks like it's running. Okay, looks like it's good. It's 12 seconds done. So let's take a look at our results and see what happens. Here is our DSS view and then db.dss. I'm going to click on View and then Refresh Catalog. Boom, here are all our decision variables. So you can see we have our channel flows, that's what we have most of, and then our demands, reservoir volume, and then a couple slack variables. Let's check out the reservoir volume. So I'm just going to look at the plot right here. Remember the horizontal axis is 100 years. So to get any detail, we kind of have to drill down a little bit. And it looks like our reservoir is actually going empty for some of these months, which is fine. I didn't try to set different zones and priorities with regard to storage within the reservoir, except for that target elevation. But in reality, I would have a dead zone or an inactive zone at the very bottom, which is like the highest priority cannot be violated, as well as some other lower zones, which can only be violated for the purpose of satisfying some very important in-stream flows or some demands downstream of the reservoir. But anyway, we can see how the wet and dry portions of the year kind of fluctuate and how that affects the reservoir storage. So that's cool to look at. And I don't want to look at too many stats right now, but what I am interested in, like I said, was the flow and the demand and the water reliability to farm 3. So let's go ahead and look at farm 3. Here's the total flow to farm 3. And then this is the priority 3 and priority 5 allocation to farm 3, where we have a target of 3 and 8 CFS round the year. We're not changing the demand over the course of the year. We could do that. We could change a lot of things, but let's just see what this looks like. All right, here's the plot. Just by looking at the entire 100-year time frame, we can see that the total flow of green tops out at 11 CFS. That's good. That was the maximum. Yellow tops out at 8, and then harder to see, but red down here tops out at 3. So 3 represents the priority 3. That's the higher priority and more likely going to be fully satisfied. And then yellow represents priority 6, which is the 8 CFS. I'm going to go ahead and zoom in on this plot a little bit. Okay, let me zoom in a little further. So here in red is the priority 3 for 3 CFS. And you can see that that is satisfied most of the time. Looks like it's not satisfied here. Only 2 out of 3 is delivered, 0 out of 3 is delivered, 2 out of 3 is delivered, 3 out of 3 is delivered. And then the yellow line here, 8, a little bit less reliable, but it seems to be able to deliver that 8 CFS most of the time. And then, of course, the sum of yellow and red in this situation is green, which is fluctuates between 0 and 11, basically the sum of those two priorities. If we want to take a look at the data, I'm going to go File, Tabulate. Now, most likely, we're going to have values of 11 or 0 and 3 or 0 and 0 or 8. But occasionally, we're going to have a value that's between the two, which means there's a partial reliability that the demand for that particular month was partially satisfied. Okay, there's not too many of them. Here's one, 6.06 CFS was delivered to Farm 3 for Priority 6 on October of 1959. Okay, so I'm not going to hunt for all of them, but they're out there. Next, what I want to do is try to quantify the actual reliability of this water supply to Farm 3 based on the priorities. So I'm going to select just Priority 3 and Priority 6. I don't need the total. I'm going to click on the table button right here, and then I'm going to copy and paste all this data. There's probably other ways to export, like through Excel or whatever, but I already have an Excel table set up. So I'm going to Control C to copy, and then come over here to my Excel, and then I have a separate tab here for results. So I'm just going to paste in the numbers right here. This is my trial 1, priority 3 and priority 6 on a 1-month time step. If I scroll down here to the bottom, I sort of have a results. So this is the very end of the simulation. This is the final month here, C1200. And then here are my totals. So in the priority 3 column, let me zoom up a little bit. In the priority 3 column, we have a total and an average flow. So out of 3 CFS allocation, we're delivering on average 2.79. Of course, it's going to be 3 or 0 most of the time, but sometimes it'll be between 0 and 3. Anyway, the average is 2.79, and then that quotient maths out to 93.0%. As for priority 6, we are demanding 8, but on average, we're getting 6.05, and that comes out to 75.6%. So a grand total shows right here. The average is 8.84 out of 11 is 80.4%. You could quantify that in a very crude sense as the reliability to Farm 3 under these conditions. Next, what I want to do as sort of an if-then statement is to see how this water reliability to Farm 3 would change, most likely increase, if we increase the reservoir size, specifically the reservoir target volume. So what I'm going to do is come back to my files here and click on reservoirs. So instead of a maximum capacity of 25, let's increase it to 35. Let's make the target 30 instead of 20. So in 20 up to 30, we're increasing our target volume 50%. Let's go ahead and save that, rerun the model. One more thing I want to do though is also reset the initial storage. So init.dss, edit, and then I need to change these values, from 20 to 30. Okay, that looks good. And then file, save. Okay, thank you. Close, and then back to WRIMS. Let's go ahead and right click, run as, and then run. Okay, that ran only 8 seconds, so that was fairly fast. It's a simple model, so that makes sense. All right, back to DSS view, back to the dv.dss data view, refresh catalog. Now, if I look at the reservoir storage, it should look a little bit the same, except, yeah, pretty much the same. It looks like the reservoir is draining because it starts way up here at 30,000 acre feet, and then it drains. So we probably don't have any shortage for the first 5 years or so. Anyway, just an observation. Let's go ahead and take a look at the flow to Farm 3. Okay, so let's look at the plot first. Boom. Really pretty much looks the same as we saw it last time. I'm going to deselect the total and just look at priority 3 and priority 6 in the table view, which is right here. As before, I'm going to highlight all the data, okay, and then Control C to copy, and then back over to Excel. Over in the right column here, I have a trial 2 setup, which I've labeled with the enlarged size, the target of 30,000 acre feet, and then paste. And then let me scroll down to the bottom and see how this compares. Okay, so very little difference, to be honest. Instead of 2.79, it's 2.8 for priority 3. Instead of 6.05, it's 6.09 for priority 6. So instead of a total of 80.4, it's 80.8, which tells me that increasing the size of the reservoir isn't the limiting constraint. What's really the limiting constraint is the amount of inflow. We don't have enough inflow, and why we saw that reservoir drop down to bottom out a number of times throughout the simulation. So that's interesting, and I think this result would be a little bit more satisfying if we had more inflow. So let's go ahead and do that. I'm going to come back up to the top here and then just change that, zero out my trial 2 data. And what I'm going to do is come over to inflows. Now, this inflow averaged 125.25 that I've synthesized, or 125.203, for instance. What I've done is increase these average values by 5. So now it's going to be an average of 130, and we shouldn't see the reservoir bottoming out as before. So I'm going to generate a new inflow time series for 100 years. And by the way, if you had thousands or millions of years to simulate, you could do that. That'd probably be a little bit more accurate. But what I'm doing here is just using 100 years and also neglecting edge effects. So I'm even using the first year of data, which is fine for this example. But in reality, what you want to do is truncate any potential boundary conditions like initial effects or even final effects the last few years or first few years, which could affect your results in an artificial way. Okay, so I'm going to paste this new time series dataset data into my inflow file. Okay, here it is. I want to go right click and edit, and then I'll just paste right here. Okay, file, save, okay, and okay. We have new inflow. What I also want to do is go back to the init file and change the storage back to the target of 20, our initial starting storage of 20 CFS. Okay, so that's good. File, save. Okay. And then I also need to go back to the reservoirs and set the max capacity to 25 and the target to 20. Okay, so with everything saved, let's go ahead and run the simulation. So basically what we're doing here is comparing the original with about 125 average CFS to what we're doing here with about 5 more CFS to see how that affects the hopefully improved reliability of flow to satisfy the demand at Farm 3. All right, that finished up, and dv.dss is right here. View, refresh. Let's take a look at the reservoir plot right here. Okay, this looks a little healthier, if you know what I mean. It starts at 20 and it drains, but it looks like it's getting at least half full. It's getting back up to at least 10,000 acre feet a number of times. All right, and then back up to our flow to Farm 3 for Priority 3 and Priority 6. Here is the table data. Once again, I'm copying that to my clipboard, Control C, and then back over to Excel. Here is our results and paste. Okay, let's scroll down to the bottom and see how that compares. Oh yeah, much better. So we have 93% has improved to 98.7% for that priority demand of 3 CFS. And then for priority 6, 8 CFS demand, we have a 90.4% reliability. So the overall reliability increased from 80.4% to 92.6%, all because of an increase of 5 CFS inflow in our time series data set. So I'm going to copy that data from that we just ran. I'm going to call that the new trial 1. Okay, that's in. And then let me delete that data from trial 2. So if I scroll down again, I have my 92% right here. The last scenario I want to run with this particular exercise is a water rights transfer scenario. And what's going to happen is Farmer 3 wants to talk to Farmer 4 about buying his priority 4 allocation. And in exchange, Farmer 3 is going to relinquish his 4 CFS at the same amount of priority 4 down here in priority 6. So, one second. I have a slide for this. These are the two different allocations that Farmer 3 currently has, priority 3 and 6 for 3 CFS and 8 CFS. He wants this 4 CFS as well, and will give up 4 CFS down here in exchange, plus probably a ton of money. So what that looks like is this is the original on the left. This is the proposed after the water rights transfer agreement has gone through. You see Farmer 3, priority 3 is now 7, so it increased from 3 to 7, and that was sold from Farmer 4, priority 4, which decreased from 4 down to 0. And then further down in the allocation table, Farmer 3 sold his 4 CFS, so 8 minus 4 is 4, and that went to Farmer 4, who gained 4 CFS, so 9 increased to 13. Okay, so we need to make a few changes, but not too many, to replicate what's happening here. And those changes are going to be in the demands file. So here is our code. Here is the demands. And then here are the actual demands and the priorities. So we're going to stick with 102. And then instead of 3 here, we're going to increase this to 7. So it added 4. That's Farm 3. And then in result, the swap is going to be a 0 right here for Farmer 4. Now you may say, why do we need this at all? Well, I mean, maybe we don't, but it's the quickest way to make the change and run the model. All right, priority 5 is still 7. Now priority 6 is going to drop down to 4, and then priority 7 to farm 4 is going to increase to 13. All right, so let's go ahead and save and then rerun the model with those new numbers. Go right click and run as. Okay, that finished up. Back to our decision variables and refresh. Let's take a look at the reservoir storage. So I like looking at this one. That doesn't, yeah, that wouldn't change actually. Let's take a look at the farm 3 flow to satisfy priorities 3 and 6. So let's actually highlight all 3 and look at the plot first. Here's priority 3. That's up to now 7 CFS. And then priority 6 is down to 4 CFS, and the sum should still be the same of 11 CFS. Okay, that looks good. Let's take a look at just these two paths, and then here is the data. So we have 7 and 4. Okay, I'm going to Control C to copy, and then come over here to my results and paste that in. Then let's go ahead and go down to the bottom. Okay, I also have to update the allocation. So instead of 3, it's 7. Instead of 8, it's 4. So previously, the 3 CFS allocation for priority 3 was satisfied 98% of the time. 7 CFS allocation for priority 3, when we bought the new rights, is satisfied 98.0% of the time. So almost as reliable, and that makes sense. In fact, the 4 CFS down in priority 6 is satisfied a little bit more often than the 8 CFS from priority 6 in the previous run. Altogether, the total reliability increased from 92.6% to 95.7% as a result of that water transfer made between farms 3 and 4. All right, well, that was it for this exercise. What we did was build a model with a inflow, a reservoir, a few demands, and a priorities table identifying the allocation and the priorities for each of the demands. We ran the simulation, and then we ran it a few more times by increasing the flow rate, increasing the reservoir size and target storage, and then performing a water rights transfer, and then looking at the results from the model.